Hi, Jessica and Ella. Let's see. Well, we got lots of people coming in here. Uh, Haley, there was somebody else. Who else was in the waiting room? Brittany. Okay. Yeah. You're on there, Sylvia.
Hello.
Good morning.
Morning.
Wonder why you always pop up. You're always the one that pops up. And you're not always even the first in. You're just always the one that pops up.
Interesting.
Okay, Haley. The audio is messed up. Let's see. Let's see if I can figure it out. So, Haley, can you hear me at all? Audio is messed up, so I have to use chat. Okay, we can do that. Okay. I can hear, but in my other Zoom meetings, people haven't been able to hear me. Okay. All right. That's good. Okay. We've got Allison, Brittany, Haley, Ella, Jessica, Sylvia. How are you guys doing this morning? We're a week away from the end of classes. This is like the longest half semester I ever had in my life. I mean, it hasn't been longer. Actually, it's been a week shorter, which is really boggles my mind because it doesn't seem like that. So anyway, everybody should have their test back now. Is there anybody that did not get your test back? Because I sent it back as soon as I graded every one of them, I kind of sent it back. There's one thing I did want to ask you about. I have your second test because if you remember, you took it before spring break. I graded it by hand. And I might have talked to you Monday about what I needed to do. I need to get it to you one way or the other. And when I looked at the pile and thought about scanning anything else, I was just like, I don't want to scan anything else. So what I want you to do, I think, is send me over email your Surface Mail address, and I'm just going to send you a hard copy of the test. It just seems like the best way to do it at this point. If anybody else has got any other ideas, but I want you to have it. Then you'll have all three. You'll have all three tests, and then presumably most of the homework. So that ought to get us sort of caught up. This we've still got people getting in here. Okay, so once again, for the couple of people that came in a little bit late, there we go. Send me over email today, and I'll try to get it mailed out, by the end of the week. Your Surface Mail address, and I'll just stick it in a manila envelope and mail it to you. Okay, we need to support the U.S. Postal Service, or somebody's gonna kill it dead. So there are people who depend on the U.S. Postal Service. Okay, questions? Anybody? Anybody got any general questions? Okay, Ella, you sent my test tube over email. I did? Really? Okay, let me see what I got here. Did I do that for everybody? I can't remember. I really can't remember what happened before the fall. Is there anybody that doesn't have their test tube? Just speak up or chat, or probably best to unmic and just tell me. I will say this: if you've got it, don't worry about sending me your email, or just send me an email and say I have it. That's probably the easiest thing to do, so I'll know and I won't worry or wonder. And if you don't, I'll mail it to you. Let's just do it like that. We'll do it like that. All right. Everybody good with that? Okay, let's see. Let me see where I got too many things going here. I got the chat going. I got everything going here. All right, so there we go. Let's see if anything comes up. Okay, so we're on the last thing I want to talk about, and that's springs. And we did the introduction on Monday. If you have not gotten the homework to me on there was one systems of equations problem, and there was one nonlinear equation, please get that to me. I have not started grading them yet, so I will take them until the time I start grading them, and that'll probably be this afternoon. Okay, so I'll get all that back to you. As far as the springs go, there are a couple of problems in the book that sort of put you through all the paces on a springs problem, and I'm going to go through one completely today on free undamped motion. I've got damped motion left to talk about and driven motion. I probably will be able to finish that either on Friday or very early on Monday. Am I right that reading day is technically Thursday? So we would have class Monday and Wednesday. I think that's what happens. We won't do anything on Wednesday. I will have what I'm going to do finished up Monday early. And by the time when I get this next homework graded, there might be one really short homework on springs, or just, I'll decide about that later. But I should have, in general, I should have your average done. And if you remember, what I said was, and this will be different from everybody, because some people chose to have a grade in the course, some people chose to take it pass, no credit. As I said, anybody that's happy with their grade after I finish the averages before final exam period starts, you don't have to take the final. If you need a grade to replace a lower grade potentially, you can take the final. The final, again, will be open note, open book. I mean, the first two tests weren't, so that should make that a little easier if you see what you've done wrong and so forth and so forth. All right, Christina's waiting to get in. So that's sort of the way I see the rest of the next week. Anybody, let's see if anybody's chatting with me here. Anybody questions, anybody about any of that? Let's make sure I got Christina in. Yeah, I got her in. You there, Christina? I think so. Yeah. Okay. So questions, anybody? Okay, let's look at follow up on what we started on Monday and talk about springs, and just look at a spring problem in practice here and see what we've got. Let's see. All right, there we go. So this first part of what we're talking about sort of lays the groundwork for most of it. Is free undamped motion. We'll see sort of at the end of this lecture that it's not very realistic. I mean, if you think about free undamped motion, you think about a spring that just keeps doing the same thing over and over and over again and never stops. That's typically not the case. Might be true in space where there was no gravity, or different situations, but it's not very realistic. So I'll finish that up today, and then the next the last thing I'll do is damped motion, all right, where you do have some forces, some external forces acting on the spring. So what I want to do today is just go through kind of a whole problem about how we're gonna look at this free undamped motion. Okay, so let me just let's just review what we did yesterday. When we looked when we set up an equation yesterday, we looked at this equation of motion, or this equation that had to be solved. That was the equation for undamped motion. Okay, what that is simply a dE second order with constant coefficients. So it's really nothing. It's got all the different variables in it, but it's nothing unusual for us to be able to have to solve. So we did make sort of this one substitution right here, this omega squared, which in most problems you're going to have to figure out. And you figure out omega squared by simply knowing the spring constant and the mass, okay? Some other things that we talked about. So when you define this coefficient on X here, it'll be spring constant divided by mass. Other things we need to think about, weight is mass times gravity, whatever, gravitational pull, whatever system you're looking at. Where we will use this most often, guys, is that we need this M right here to write the equation. And often they'll give you the weight of something and you'll have to find M. The weight has to do with gravitational pull. Mass is something different, but you'll have to find that by putting the weight over whatever gravity is. If we're working in feet or feet per second or whatever, gravity will be 32, so on and so forth. We're in meters, it'll be 9.8. But you'll most likely have to find that in order to get this omega squared right there, okay? And K, the spring constant, we got from Hooke's law. And remember that Hooke's law yesterday said F was K times S, that force exerted by the spring in the opposite direction of gravity when it's going up, and then the other way when it's going down. K is the spring constant, S is the amount of elongation, and that's the force. Typically, what'll happen here is they'll give you the force, and they'll give you how long it got stretched, and you'll have to find K. Right? A couple of other things we did. The period was, when we solved this thing, was 2 pi over omega, and the frequency was just the reciprocal of that, omega over 2 pi. So let's set up one of these things and go all the way through it. So here's my problem. It says a mass weighing 2 pounds stretches a spring 6 inches. At time 0, the mass is released from 8 inches below equilibrium. 8 inches below equilibrium with an upward velocity of 4/3 feet per second. Determine the equation of motion. Now, let me start off by saying when you read these problems, you really, really want to look at the units, because you need to have everything in corresponding units based on all the different things you're being given. The one thing I see here is these things are in inches and your velocity is in feet per second. My gut reaction here is it's easier to change inches to feet than it is to change this feet over here with the velocity to inches, okay? So one of the first things we're gonna do is change the 6 inches and the 8 inches, okay? So, so we got 2 things to find, because remember, we're trying to find this thing right here. We need omega squared, and omega squared was K over M, where K was the spring constant. Okay, so let's find the spring constant first. Hooke's law says that force is K times S, and the force here, a mass weighing 2 pounds, it's the 2 pounds that stretches the spring. So that's, I'm gonna put a 2 there for the force, is equal to K, whatever the spring constant is, times the amount of elongation. The amount of elongation in this thing is 6 inches. We said we were gonna be careful to change it, so I changed the 6 inches to 1/2 foot. And I got, when I do this thing, when I solve this for K, I get K equal 4. So that's the first thing I need to know. I need to know the spring constant for this thing. Okay. The other thing I need to know is the mass. This is what I was talking about just a minute ago. This force attributed to weight is mass times g. That's just a way to say force equal mass times acceleration in this case. So in this case, it's weight. That means mass is the weight over the gravity in this case. So the weight of let's see, a mass weighing 2 pounds. So I put the 2 right here. And gravity for us, since we're in feet and seconds, is going to be the 32. When you're measuring mass with feet and pounds and so forth, you're gonna what you look at is that mass. The unit is a slug. Okay, that's, I mean, whether you call it something or not, that's what M is going to be. So in this case, 2 over 32, that's going to be 1/16. So if we look at what we've got, this omega squared that we put as the coefficient on x right here. Remember, it was the second derivative of this equation of motion, x with respect to time, plus omega squared x. Omega squared, we said, was going to be k over m. We've determined that our k was 4. So this 4 right here comes from that. And the mass was 1/16, which we got from the weight and gravity. Okay, so 4 over 1/16 is equal to 64. Okay, so that's where I am. Here's the equation I'm trying to solve, and for us, it's a pretty easy equation, and it's all the stuff that we did on the last test. Okay, so anybody questions about how I got that? The rest of this lecture is going to be, what am I going to do with it? How am I going to graph it? Well, first of all, how am I going to solve it? What's the easiest way to graph it? What are the important things to know about this equation of motion? Everybody okay with that? Okay. So what I come up with here, I can do a couple of things here. Remember, I could find the period. All right. And the period was 2 pi over omega here, and omega squared was 64, so that says omega is 8. So the period of this spring, all right, is pi over 4, or this equation is pi over 4. Frequency is 4 over pi. So essentially that means things happen, if the period's 4 over pi, the frequency, pi over 4, sorry, and the frequency is 4 over pi, that means this, this motion happens 4 complete times in pi units. All right, 4 complete times in pi units. Okay, now let me just sort of give you a preview of what we're trying to do. We talk about this equation of motion like this. X of t is the equation of motion. So it's, I don't want it to be confusing here, but that t is the independent variable, and x is what we would think of as y. Okay, it's the dependent variable. That's what it's going to look like. So let's solve the equation. That's something we know how to do. So there's the equation. First thing you do, get a characteristic equation. Okay. Some of you had a few problems on getting characteristic equations on the test. That's based on how long we spent on the characteristic equations. That was like the whole chunk middle of this course. Okay. So it's what we basically did from the time we came back from break until, a week ago. So my equation of motion, not my equation of motion, but my characteristic equation is m squared from the x double prime plus 64x. When I solve that, plus 64, and the 64 comes from the coefficient on x. When I solve that, I'm going to see that I get imaginary roots, where the real part of that is 0 and the imaginary part is 8. What we know what that looks like. That looks like x of t is c1, whatever that parameter is. I don't know exactly what it is, but cosine 8t, that's the omega there, or the imaginary part of the root, plus c2 sine 8t. So I could have given you that equation. I gave you something that looked like that, actually. I think we had one on the test that looked almost exactly like that, except I think maybe this was a 1t here, or a 1x. So now I need, for this particular spring that I've got, I want to find C1 and C2. So I need to go back to the conditions that will allow me to find that. Now, the first condition was this 8-inch thing. And let's go back and see what that 8 inches was. If you look back at the problem, it says at t equals 0, the mass is released 8 inches below equilibrium. Now, things are going to seem backwards here when I start to do this, but if you're released below equilibrium, that means the spring has lengthened, okay? So you think about that as a positive thing. So if I look at that as a condition here, it says that the 8 inches, remember, was 2/3 of a foot. So we had changed that, and we need to keep it changed. All right, so 2/3 of a foot. That says that at time 0, when t is 0, the position of this thing is at 2/3 feet. Now, again, I'm going to keep saying this because it it just seems so backwards in a way. But this is a positive number. You've pulled it down, but when it gets graphed, what's going to get graphed is the 0.02 So it's going to look like when we graph it, it's kind of going to start. I looked at this thing. It's going to start up here at 2/3. All right, the graph is going to look like that. So if it's below equilibrium, the spring is sort of longer. I think about it like that, and it starts up like that. Okay, so it's sort of backwards. We're going to draw a whole picture of it later. It seems sort of backwards. Okay, so the next thing, I can find C1 there because the cosine of 0 is 1 and the sine of 0 is 0. So that tells me that C1 is 2/3. So I've got that. Now, the other condition, let's go back and look at what the other condition was, and then I'll come back here if you need to write that down. But if I come back, the other condition is it's given an upward velocity. It's given a push. It says with an upward velocity of 4/3 feet per second. So in other words, we've got the spring, say, down here. There's the spring. There's the mass on the thing. We push it up. You push it up, okay? And when we push something up, it's working against gravity. That means the velocity is going to be negative. So when I look at that condition, and again, it says it's pushed up with an upward velocity of 4/3 feet per second. They're not going to give it to you in the problem. This is what's going to tell you what the sign is. If you do downward velocity, it'll be positive. But if you push it upward and it's working against gravity, what's going to happen here is that this minus, it's going to be minus 4/3. In other words, at time 0, I'll write that right here, at time 0, the derivative, that is the velocity, is minus 4/3. Okay, you have to keep that straight or you're going to get the wrong coefficients, and that'll be a problem. So one thing I need to do, question anybody about that? Okay, one thing I need to do is take the derivative then. Well, there was x of t. If I take the derivative, it's just going to be C1 minus sine 8t times minus 8. So right there. This will be C2 cosine 8t times 8. There's the velocity. In order to figure out what the other thing is, and I had already found C1 here, guys, I am simply going to plug in 0 to this x prime, to this velocity function. If I plug in 0 there, that drops out. So that's gone. Sine of 0 is 0. This is 1. So I get C2 is minus 4/3. Let's write it right here. C2 is minus 4/3 divided by 8, which is minus 4/24. And that's where I got that minus 1/6 right there. Okay, so no C1 and C2. So that's all the information you kind of suck out of the problem. And technically and theoretically, you have got all you need. You've got the equation of motion. It looks like that. Okay. So, question anybody about that? Now, great, I've got an equation of motion, but it's not in a very nice form. In fact, it's in a terrible form. For instance, if I said to you, I want you to find the amplitude of this trig function. You know, when we look at amplitude, if you remember, and this, I'm getting ready to go heavy into trig here, guys. So stop me if you've got a question, but I'm going to sort of look at all the stuff you had in pre-calc about trig and stuff you used in calculus and so forth. If you look at a function that maybe was a trig function, and I said y, let's go over here. I said y is equal to 5 cosine t. What's the amplitude of that function right there, guys? Y equal 5 cosine t. What's the amplitude? Anybody? Unmic and tell me what the amplitude is. Maybe I need to think about what amplitude means. Amplitude is sort of the farthest distance something goes away from a central line in your graph. So if I were to graph, I didn't leave a whole lot of room here, but if I were to graph this thing right here, the biggest the cosine ever gets is 1. So the biggest this thing is ever gonna get is 5. So it would, knowing what a cosine looks like, it would start there at 5. It would look like that. Its low point would be at -5. So what is its amplitude? What's the furthest it travels on either side of this middle line here? What is it, guys?
5.
5. Yeah, it's 5. So even if that were a negative, all it would do, the amplitude is still 5. An amplitude's a positive thing, guys. If it were negative, the thing would have just looked like that. It's still the distance away from here to here and here to here is still 5. Okay, so it doesn't really matter what happens there. So in general, you look at the coefficient, at least when you're looking at sine and cosine. All right. The other ones, well, sine and cosine, you can tell by just the coefficient. Okay, or I really should say the absolute value of the coefficient. So looking at that form right there doesn't look anything like what I need it to look like to read off the amplitude. Now, of course, we could probably derive a formula for it, which is exactly what we're going to do here. Well, we're going to put it in a nicer form. Another thing I might ask is, where does this thing cut through the axes? In other words, if I'm talking about spring, where does it go through? You know, if that's the resting position right there, that dotted line, at what times does it go through equilibrium? All right, in other words, where it would be if the spring were at rest. So I might need to know amplitude, how high it goes. I might need to know the times where it crosses the axis, all right, where it goes through equilibrium. I might also need to know the extreme displacement. Now, extreme displacement is what's the highest that this thing goes, and the amplitude is gonna help me with that. All right, but if I need a time for that, suppose this was a curve from Calculus 1, and I wanted to find out, that would be a local max right there. Okay, how do you find local maxes and mins, for that matter, in calculus? What do you do with the function? What do you do to find a local max or a local min? Anybody?
Where the first derivative is 0.
Yeah, exactly. Where the first derivative is 0. I can tell Allison's been tutoring in the Quest Lab, because the Calc 1 students always come in and they don't get that at first. Okay, so we would find, and we call that finding the critical number, and then we could determine whether it was a max or min, determining whether it was going up and coming down or going down and coming up. Okay, so there's a lot of stuff we've got here, and that's, I mean, I could take a derivative of this, but again, the way we find that is to set that derivative equal to 0, and if I took that derivative, which I had already done up here, there's the derivative. Whoops, where'd it go? There's the derivative right there. If you set that equal to 0, it's not going to be very easy to solve for t. So, long story short, I need a different form for this. And the form that you will see most books and physics books and all kinds of books alike, that we're going to put it in, is going to start with this form where we solved it. I mean, we're going to come out with that form, okay? That's the form we're used to looking at when we solve these things, because we know if it was an imaginary root, it's going to come out with a cosine and a sine and parameters on each one of them. I want to put it into something called amplitude form, right? And amplitude form, the definition of amplitude form looks like that. Now, there are some things you see that you recognize. There's some things you don't. The omega you recognize. So remember, in the one we were looking at, our omega was 8. Okay. So the omega in this one is going to be the same there. It's going to be 8. A is actually going to be the amplitude of this thing. All right. When I put it in this amplitude form, that's a sine function. It never gets any bigger than 1, no matter what you're taking the sine of. So the highest it rises will be A, and it'll go down that equal distance, or vice versa. Okay. Now, this thing right here is the thing you might not know what it is. this this thing right here is called the phase angle. And that's the thing that's probably a little bit hard to find. But I want to define some of these things. And I want to show you the relationship between this equation and that equation. And essentially, I want to show you that for particular values of A and the phase angle, whatever, these things are going to be exactly the same. In other words, this one right here is going to be exactly the same as that one right there. Okay. Now, here's what I'm going to try. I'm going to say, well, I want it in this form. How could I, first of all, make it look a little more like that form? I'm sort of going to play backwards here and see what I have to do to make things look alike. Well, I'm going to use some trig here again, guys. That's the sign of the sum of two things. Now, whether you remember it or not, you can go to the back of your calculus book or wherever, and you got a formula that says this. It says the sine, oops, my pen's coming apart. The sine, get rid of that. The formula we're going to use is this. The sine, maybe, the sine of two things, A plus B, is sine A cosine B plus cosine A sine B. That's just a sum formula. And I can tell you, when I came out of college, I had to look that thing up. But then when I got to grad school, we had this guy who was, he must have been about 80. I don't know. He was head of the teaching assistants. And we were all teaching pre-calc or calculus. And so we were having to teach these things. And he had this weird looking little dance that he did. And he had a song that went with this. And to this day, I cannot get that out of my head. He's seeing an 80-year-old in front of me jumping up and down and singing a song about the sine of A plus B. So I know it because of that. But you're not going to know it because I'm going to sing it because I'm not. But anyway, that's the formula we're going to use. So let's do it here. If I say there's A, I'll just leave the A there. That's just a constant. And I use the sum formula. It'll be the sine of the first, which is omega t, times the cosine of this phase angle, phi, all right? Times the cosine of that plus the cosine of the first, excuse me, which is omega t, times the sine of the second, which is the sine of this phi right here. So let's see what would happen, what would make this look like this amplitude form look like this other thing. What would make it look like that is the following. And we're gonna get some information from this. We're gonna say, what if the sine of phi, well, let's do this. What if A, I'm gonna write that down here. I've got it somewhere else, but I'm gonna write it here. What if A were the square root of C1 squared plus C2 squared, all right? And that's what A is going to be. And that those C1 and C2 are just the things that come off that original solution, the parameters that I found. And we're going to let this sine of phi right here be equal to C1 over A. C1 over A. Right, so there's A. This is C1 over A. We're going to let the cosine of phi be C2 over A. C2 over A. Now, it's not hard to see that if I multiply that out now, the A's are going to cancel and leave me with a C2 on the sine. And when I multiply times this piece, the A's are going to cancel and leave me with a C1 on the cosine. And that's exactly what I want. So if I define these things like this, A is that, and that's the sine, and that's the cosine. These two things are going to be the same. Now, here's the trick. And we'll go through and do this for that particular problem I've got. But here's the trick. If this is the sine, and that's the cosine, I can sort of draw a triangle here. It maybe helps to remember. C1 over A, which is this thing. Actually, if you have C1 and C2 on the legs of your triangle, by the Pythagorean theorem, the hypotenuse is just going to be the square root of C1 squared plus C2 squared. So that's my A, okay? And this is the opposite side. So the sine of this phi that I'm looking for, this phase angle, is going to be C1 over that A. And the cosine is going to be C2 over A because it's adjacent over hypotenuse. Opposite over hypotenuse, adjacent over hypotenuse. Something that tells me that's very nice then, if I put sine over cosine, I would get tangent. If I inverted and multiplied here, sine over cosine, I would get C1 over C2. There is a way right there to find out what the phase angle is. Again, I'm doing it generically, and I'll do it in particular for this other one in a minute. So, so that's what I just said is what I did right here. I said, well, if this is A sine, and I played all this out with the sum formula, and I put my sine, I put my C2 over A here and my C1 over A here, and I get the same thing. I get the same thing with all of these caveats here. This is the sine at C1 over A. Cosine of phi is C2 over A. Right? Now, remember, this is a little bit backwards. Remember when we go, I'm going to go back and look at the original equation here. The C1 was the coefficient on the cosine. The C1 was the coefficient on the cosine. The C2 was the coefficient on the sine. So when I start solving these things here, guys, I'm going to need to remember which one is which. Okay, so once again, C1 is the one on cosine, C2 is the one on sine. Okay, even though it looks sort of backwards from where they came from. All right, so let's go back. Let's go back to my problem and see if we can find all these things. Okay, there was my original equation here. Let's see, get a little red ink here. My original, when I saw this thing, and it was in this form that's, it's the equation of motion, but it's not very helpful to me. C1 is 2/3. C2 was -1/6. C1 is on cosine, and C2 is on sine. Okay, I can find A because we said A was going to be the square root of C1 squared plus C2 squared. Okay, that's my A. And when I do that, I square the 2/3, I'll get 4/9. I square the -1/6, I get a 36. Change this to 36. I get 17 over 36 under the square root. The denominator's nice, so the square root of 36 is 6. And I get the square root of 17 over 6. That's going to be the amplitude of this function. That's what I need. That's going to be the amplitude of this function. Okay. Now I need to find the phase angle. And here's where we really go sort of heavier into the trig. But I've got part of this. I've got this part right here. Now, let's find out what the phase angle is for this problem. One thing you want to note is that ultimately you're looking for the angle. Because if I come back to the form that I really wanted, this form right here, right in here, let's see what we got here. I'm getting too much ink on here. But that form right there is ultimately what I want. I have already determined what A is. It's the square root of C1 squared plus C2 squared. I know what omega is because omega, we said, was the same thing that was right there. Okay, so for me it was 8. I don't know the phase angle. That's the only thing I've got left to find. So I'm going to go back to where we were. Here. Oops, whoops, went too far. All right, so here's how we're going to find the phase angle. First of all, we're going to have a calculator. We're going to set it in radians. Okay, make sure it's in radians. None of this works unless your angle's in radians. So we know that the tangent of this phase angle, because of how we defined the sine and the cosine and put them over each other, was C1 over C2. Remember that C1 was the one on the cosine, and C2 was the one on the sine. So there's, and by the way, if I solve for phi here by taking the inverse tangent, that's going to isolate phi and give me what I need, essentially. So form tangent of phi first, and then take the inverse of the tangent, and you'll have essentially what you need. Pick off the coefficients. Coefficient C1 is the one on cosine, it's 2/3. This minus 1/6 is this one on the sine. When I invert and multiply, I get minus 12/3, which is minus 4. All right. So what I have so far is that phi is the inverse tangent of minus 4. Now, let's talk trig for a minute. If we have an inverse tangent, and notice that the inverse tangent here came out negative, that's a negative angle. Let me add a piece of paper in here to remind you some things about inverse trig functions, and particularly inverse tangent in this case. So let's see if I can get an extra page on here. No, let's don't do that. That's not what I had in mind. Let's see if I can get an extra page here. Okay. All right, so I'm gonna come back to this page in just a second, but let me just review some trig here. Suppose I said I had some angle theta. I had taken that some tangent theta, for example, was minus 1. Okay. Think about the unit circle and tell me a couple of things here, guys. If the tangent is negative, what quadrants do you have to be? There are 2 quadrants you could be in. And what are those quadrants? If the tangent was negative, what quadrants could you be in here? Anybody? Unmic and tell me what quadrants you're in if the tangent is negative.
The second and fourth.
Right, second and fourth. All right, so I know right here, because remember it's sine over cosine. And the cosine's negative here and the sine's positive, and down here, the sine's negative and the cosine's positive. So I could be in 2 and 4. Now, I think you could also tell me that, that theta here, well, let me ask it this way. Do you know, think about the unit circle. Do you know a place where in quadrant 2 where the tangent is minus 1? Let me ask about the first quadrant first. And you can give it to me in degrees if you want to. We'll change it to radians in a minute. Where's a place in quadrant 1 where the tangent's 1? Think about the fact that the tangent is sine over cosine, guys. Where's a place where that's sine over cosine would give you a 1?
Pi over 4.
Yeah, pi over 4. So for instance, if we were in the unit circle here, well, that went away. Let's try again. All right, if we were in the unit circle here, we'd have a point right there that was root 2 over 2, root 2 over 2. And we know that's pi over 4. So that would be the radians there. Now, where's that right here? What is the angle right here where it would be minus 1? If it's pi over 4, say it again.
3 pi over 4.
Yeah, it's 3 pi over 4. It's 3 pi over 4. Now notice that pi over 4 is this angle right here in the first quadrant is a reference angle for that. In other words, that reference angle right there, we'll call it theta 1, whatever. That reference angle right there is what you get this angle that you need by saying pi minus that reference angle. That'd be 3 pi over 4. Hey, what's the one down here going to be? What's the one down there going to be? We got a pi over 4, 3 pi over 4. Just count them. 4 pi over 4, 5 pi over 4, 6 pi over 4. That was, yeah, that would be 7 pi over 4. Right. So the angle there will be 7 pi over 4 because one of them's negative. One of the root 2 over 2 is negative. The other one's positive. So now here's what happens. somebody find, let's see, let me find on my calculator here, I'm gonna find the decimal representation for pi over 4. It's 0.7854 if I round it. So pi over 4 is 0.7854. Okay, and that's in radians. So it's 0.7854 radians. Okay, now here's what I want you to do on your calculator. Just a minute ago, I said I was going to find this angle that I needed, that theta, by taking the inverse tangent of -1. That's how I find it. If I know what tangent is and I want to find out what the angle is, I'll take the inverse tangent. Tell me, guys, make sure your calculator's in radians and tell me what you get there. What do you get from the inverse tangent of pi over 4? I'm sorry, not pi over 4. Inverse tangent of -1. Sorry, I said that wrong. It's inverse tangent of -1. We're trying to find out what the angle is. What do you get, guys? What do you get when you on your calculator when you find
pi over 4?
you get negative pi over 4 or negative 0.7854. You get negative 0.7854. Now, what is being given there is what your calculator is using as the restriction for tangent. If you think about tangent, and again, this is like a crash course in inverse trig functions. If you think about tangent, it has these asymptotes at pi over 2. The next one's going to be at 3 pi over 2. And that next thing's going to look like that. This is not a one-to-one function, guys. This is not a one-to-one function. I have to restrict it if it's going to have an inverse. Okay, so the restriction on tangent, on inverse tangent, is that you have to find an angle between pi over 2 and minus pi over 2. So that's the restriction that your calculator is working with. So when it sees a negative, it pops to that fourth quadrant, but there's one more caveat. I cannot get to that place I cannot go out of this restriction. So I have to get there from my standard position by going backwards in a sense. And if I go backwards, I get the minus pi over 4. So your reference angle is this 0.7854, but it came out minus because we're interested in having a one-to-one function. We're restricting it, and that's why your calculator did that. It would not go over here to 7 pi over 4. It would go over here to minus pi over 4. Okay, why does that matter? All right, questions anybody about the trig? So I'm going to go back and talk about why that matters and what I'm getting ready to do. Okay, so when I did this, when I found out my inverse tangent was minus 0.325817, what I was really finding is, look like right down here. Here, look right in here. I was really finding a reference angle for all the angles I'm interested in. So the reference angle for this thing is, now reference angles are positive, guys. So your reference angle is 1.32. I mean, the minus indicates which way you had to go from standard position to get there. Remember, negative angles are negative if I go clockwise, and they're positive if I go counterclockwise. Lots of trig in physics. And that's why a lot of people just kind of throw up their hands with physics because they don't remember the pre-calc, okay? A lot of it's got to do with calculus, but a whole lot of it's got to do with trig. So that's my reference angle. My absolute value is my reference angle. So what I really want to do is put it as a positive angle in the appropriate quadrant. And the appropriate quadrant here is going to be the second quadrant. I just find the first place. I say use the first positive angle for which this is the reference angle. That's how I'm going to find this phase angle. So if the reference angle is 1.325817, which is what I picked up from the calculator here, which is what it was going which way is that? Clockwise, okay? That's the reference angle. So the angle is going to be this thing, which is simply pi minus that reference angle. I mean, all the way around to here is pi. If you take that much away from it, it'll be pi minus that thing. So my phi here is 1.816. Okay, 1.816. So essentially, guys, you're going to, on a lot of these, what's going to happen, unless both of the constants are positive, then the reference angle is just going to be the angle that you want. If both of these things are positive, it's not a problem because that reference angle is an angle in quadrant 1 where the tangent is positive, and that's okay. If it's negative, you're going to use it as a reference angle in the second quadrant. Okay, so we got this reference angle right here. This is a reference angle for phi in quadrant 2. This is one reason I like all the application stuff is it requires you to remember a lot of things. And the more you do of it, the more you remember. You're pulling from everywhere. We're going to pull from Calc 1 here. We're going to pull from trig. We're going to pull in a lot of different places. All right, so I have found phi. And by far, this is the messiest thing here. It's not terrible, but it's you know, you got to make sure you know what you're doing with the reference angle and the trig. So questions, anybody? Anybody got problems with that? Now, again, a reference angle is sort of an absolute value. So it's always just this positive thing. That minus, again, has to do with the fact that it needed to be in quadrant 4, and I was going this way to avoid going out of the restriction. Okay, so let's go back to our form again. Whoops, let's see, I'm a page beyond that now. So here's what things look like. X of t is a sine omega t plus the phase angle. A was easy. It was the square root of c1 squared plus c2 squared. There was that. The sine of 8t, omega was 8. That's that, it's in the original equation of motion. The phase angle was 1.816. Now, let's go back over what I think is going to be good for finding, and then we're going to talk about finding some of those things. It's good for finding amplitude. Amplitude is just that coefficient. That's one reason I wanted it like that. And by the way, that's about 0.687. So what this says is in this motion, the highest this thing rises above equilibrium, which will actually look like below, is 0.687, and the lowest it goes is 0.687, away from the equilibrium, the axis in the middle, where the thing is at rest or at equilibrium. All right, so it's good for finding amplitude. We'll see what it looks like when we look at the graph in a second. It's also good for finding where the system goes through equilibrium. Where the system goes through equilibrium. Now, let's think about, this is a position function right here, guys. This is where it is positioned at any time t. So if we're going through equilibrium, my position is 0. I'm neither above equilibrium nor below equilibrium. So if I'm looking at a graph and everything's are working like that, that's equilibrium position right there. Okay, that's where it's going through rest, or where it would be at rest if you were just had it hanging there. Okay, so that's going through equilibrium. Now notice that if this is t and that's x of t, then all you're trying to find is where the position is 0. Where are you that's halfway in between highest and lowest? So I want to know that I'll just take this position function that I found, this amplitude form, and I'll try to find out where it's equal to 0. Okay, more trig. This isn't hard either, though. If you've got it in this form, because square root of 17 over 6 can't be 0. The only way I can get 0 out of this is taking the sine of something that will give me 0. Now think about the unit circle, guys. Think about the unit circle. Where's the sine equal to 0? Tell me all the places where the sine is equal to 0. Give me a few places on the unit circle where the sine is 0. Anybody? Where's the first place you think about on the unit circle where the sine is 0?
0.
Yep, 0. What's the next place?
Pi.
Pi. Thank you for giving it to me in radians. Where's the next place?
2 pi.
2 pi. The next one's 3 pi. What you see here is that this thing's going to be 0 where the argument, or the angle, is a multiple of pi. Where n is an integer. I just call it pi n, guys. So, example, let's just find some of those times, or find some of those places. If I let n be 0, I get a negative time. You know what? I'm not really interested in that one. So I'm not really interested in this thing over here. I'm interested in it where time begins at 0 in this case. Okay? So I'll go to the next piece. I'll let this be T1. I'll let this be pi. So if I solve for t, it'll be pi minus 1.816. And then I'll divide by 8, and I get this. Here's the first time that it goes through equilibrium. If I let it be 2, I would have 2 pi minus 1.816 divided by 8. Somebody's got their mic on. Turn the mic off. I'm hearing some background feedback. Okay. All right. So I've got 2 pi minus that phase angle. The next time it goes through equilibrium is 0.55839. You don't have to do a whole lot of this, guys, but if you let pi be 3, it'll be 3 pi minus that value divided by 8, which is 0.951. And our time is in seconds here. Okay, so those are all times in seconds. All right, I'm gonna come back to those in a minute because I'm gonna show you some. I actually write those down. Write down as those right now because I'm gonna change screens here in a minute to show you the graph. So this is places where it goes through equilibrium. Okay, goes through equilibrium. All right, the next thing that I might be interested in is what about extreme displacement? When is it at its high point and its low points, I should say? Well, first of all, I need to find the derivative because remember how a few minutes ago I referenced the fact that you find the absolute you find maxes and mins by taking the derivative and setting it equal to 0. In other words, looking at the critical numbers. When I take the derivative of this thing, it's going to be square root of 17 over 6. My function had a sign in it, so the derivative is cosine of this thing, and then times 8. I'm not particularly interested in this case in the coefficients. I am interested in this part right here. Because if I said, right there, if I said, okay, I want to know where this is 0. I want to know what the critical numbers are. I want to know where these peaks, and a minute, when I scroll it up, you'll see a valley. All right? I want to know where those are. So where's the cosine equal to 0, guys? Think about the unit circle again. What's the first place you see where the cosine is 0? Anybody? Where's the cosine 0?
Pi halves.
Pi halves. Where's the next place?
3 pi halves.
3 pi halves. Actually, and note that you added pi every time. You're just going half a circle, but you're starting at pi over 2. So here's the way I write that. I'm going to say, well, that argument or that angle, guys, those of you taking complex know what I mean by argument, I think. This is an angle here. 8t plus 1.816 has to be pi over 2 plus pi n to give me a cosine, of something that's 0. So I start at, by the way, if I let n be 0, this would have been negative. The first place it's positive is n equal 1. Actually, at n equal 1, this was t0 right here. It was negative when I let it be 0 because pi over 2 is 1.57. When I bring that over, it would be negative. So I'm not interested in that. The next one where n is 2 would be 3 pi over 2 right here. I'll take away 1.816 divided by 8. That's 0.36. That's going to be either a high point or a low point. We'll talk about what that is in a minute. If I go one more, it'll be, in other words, if I let n be 2, that's 2 pi. It's 4 pi over 2, 6 pi over 2, which is just 3 pi. Okay, that's a 3 pi there. Minus 1.86, this is 1.147. Now, I'm going to put it on the calculator. I'm going to show you what you get, but let me just say a couple of things in general. When the calculator graphs it, its original position is right up here at 0 2/3, and that's what we should see. And it's heading up. Remember, we stretched the spring out so it seems backwards. When the graph looks like it's going down here, what's happening is the spring is headed up through equilibrium to this low point, still headed up. But then when the graph starts going up, it starts to be headed, the spring gets longer and it starts to head down again. Okay. All right, I want to look at this thing on my my grapher. So let me see if I can get it up without unplugging this thing. I think I can. I think I can share a new screen and leave the old screen up. I'm still playing with this thing, guys. At least this semester, I found lots of stuff to play with. Okay, it'll ask me for a new share, I think. There we go. Great. Can y'all see it? Or you may not be able to see it. I can probably only see it. Let me do the new share here. And let me do this and share. Tell me when you can see it. Can you see it? Everybody see it?
Yes.
Okay, good, great. Okay, so guys, here's what I did. I put in my my equation of motion. I put in square root of 17 divided by 6, and it was the sine of 8x. Now, this would normally be a t in my equation, but I'm working with y's and x's here instead of t's and x's. So 8x plus, there's the phase angle right there. So I put the whole thing in. I would yell at my students because I didn't have another parenthesis to close here. But sorry about that. I need another parenthesis to close, but it didn't matter because I was just taking the sign of this. But I wouldn't take that as an argument for a student, so I want to put the parenthesis there. And then I set my window. Guys, I set the window by kind of looking at the things I'd found, and they were small values. The amplitude was that 0.688. It was that square root of 17 over 6 thing. So I said, you know what? I don't need any more than -1 and 1 for the y min and the y max. I can see the whole thing in there. I need a little bit of leverage on the left for a negative. So I make it a little bit negative on the left. And then all those values that I found were all sort of between 0 and 1.5. All right, those were the time values right there. They're being represented by x's here. Okay, so let's look at this thing. Let's trace out and see what we get. So there's what it looks like. Now I want you to notice a couple things. I'm gonna play tracing on this thing. All right, and first thing I'm gonna do is trace up to where it started. Now, I'm not much interested in that stuff over there. That's because that's where time will be negative. But I am interested where it starts. Look at this right here. Where is it? What's its height when it first gets started into motion, guys? Look, what's the y value there? Remember, it's the x for me. But what 0.666, blah, 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 what's that look like? Looks like 2/3. Remember, that's the 0 2/3 right there. Now, when I trace back a little ways and I think about, well, where's the first time it went through equilibrium? Whoa, I went a little too far. It was at about 0.16 something, right? So that's, if you look at those values we had, it was about 0.16. Now, this thing right here means if it's going down, the thing's headed upward. If I keep going here and look at this extreme displacement point, that was the A. That's minus 0.68. I'm not going to hit right on it because of the pixels, but it was 0.688. Okay, that's the amplitude. Now, what I want you to notice here is that if I go up again, okay, there's one more place where it goes through equilibrium. The axis is equilibrium there. It's at 0.56. I think we calculated it about 0.59 or 0.55 something. So there's that. Keep going here. The amplitude, remember, was the 0.68. So there it is. It was a little higher than this. In other words, when somebody pulled this thing, pulled this thing and released it, it's going to go a little higher from where the release was, because the release was at 0 2/3, and that was at 0.66. This is 0.68. And you can see what happens the next time through equilibrium is going to be short of 1, which was about, I think we said was about 0.95. And then when we keep going again, the amplitude is minus 0.68. Okay, that's that square root of 17/6 again. Okay, and then we can keep going. Most of the problems in your book will say, well, find the first 3 times it goes through equilibrium. Or it might say, find the first time it goes through equilibrium headed up. Now remember, the graph looks sort of different from what it's actually doing in a sense, what the spring's doing, because this is indicating sort of the length of the spring and where it is at a particular time. But this going down means the spring's headed up. There's a good picture in the book of that, guys. I attempted to draw it, but I didn't draw it very well. Okay, so I want to go back. Questions anybody about what I've got? So it took a while to get to that. I'm going to try to go back to my old share, to my screen here. Let's see what happens. I'm learning. All right, I'm going to try to share that and see what I've got. All right, that's good. Okay, so I'm back here. Look, I tried to draw this picture. So when we pull the spring down, it gets plotted up here, but that's what it looks like. And it's going through equilibrium. This corresponds to that point. It's at this, quote, high point above equilibrium. This line right here is equilibrium. And the motion of the spring kind of looks like that. So it almost looks inverted. Okay. Now I want to say a word to you about this, but I'm going to say one more thing, and then I'll come back and we'll talk about that. That's just some of the homework. Question about what we're doing here, guys. Look at one more thing. I will talk about damped motion on Friday. This free, undamped motion is really unrealistic. For one thing, springs don't stay the same. When they age, they lose some of their spring, so to speak. So I'm thinking I'm anthropomorphizing springs here, because I've lost some of my spring with age. Okay, then the spring constant changes, so it may vary with age. So there are spring constants which are not just constants; they're functions of time. Depending on how old they are, they might not pull back as fast as they used to. Okay, so your spring constant would be a function of time. We don't know how to solve that. Period. We hadn't gotten that far. Take DE number 2 if you want to look at that. That's definitely not linear, and it's not a constant coefficient, and we'd have to use series to solve it. If we look to the next thing, springs vary in different temperatures. I doubt that a spring works the same way in Antarctica as it does in Miami, okay? Because what happens is that the spring constant will vary with temperature. And so this T right here, is a spring constant could potentially be a function of temperature here. That T stand in right now, usually we think about time, but in this case it's temperature. That's something called Airy's equation. So if you're a mechanical engineer, this is the kind of stuff, some of the stuff you're looking at, right? How's this spring working in this machine? What do I need to take a look at? Is it functioning in very cold temperatures in North Dakota, or is it functioning in very warm temperatures in Florida? Okay, but the point is we can't solve these now. Now let me show you what I want you to look at. You've handed in all the homework, hopefully, on and again, I'll take it till I probably won't get to solve it until to grade that next homework, the DE system and the other thing, till late this afternoon. So if you haven't gotten it to me, get it to me. It's only a couple problems, but it's still more problems to add on to your homework grade. 1, 3, and 5 are really just kind of, can you set these things up? Can you get the right equation? Can you get the phase angle right? And so forth. 11 is a good problem because it makes you go through everything. It says, what's the frequency? What's the amplitude? What's the period? It asks you all those things. It asks you some things about when it goes through equilibrium, the second time or the third time, and when it reaches its max and its min, and so forth and so forth. It's maximum displacement above equilibrium or below equilibrium. This would be displacement below equilibrium. This would be displacement above. The graph looks exactly opposite from what you think the spring is doing, okay? So, so what I'd like for you to look, I don't even know what I put on the assignment sheet, but when I was looking at it this morning, when I was looking at the lecture this morning, I looked at those problems. I think I might have assigned one last night to talk a little bit about finding the spring constant and so forth. But try those right there. This one will take you through everything, okay? And if you can do that, you can do anything I'm going to throw at you there. All right. Anybody have any questions? As I said, I don't know exactly what I'm going to do with this, with the springs. I'll probably give you, you know, a couple of spring problems to go through, answer some questions on, and it won't be on a test, and it won't be on the final. It'll just be in the form of homework that might be weighted a little more just because it's information we haven't been tested on, but it doesn't matter. It's not going to be a whole lot, but I do think it's an interesting application of the things we've solved. And you'll see it's even more interesting when we get to damp springs, when we get forces acting on those springs that make it do something different from this. I mean, normally, really, guys, when we think about a spring, we think about it going like that and then petering out eventually. Okay, that's what I'm looking at with damp springs sometimes. Anybody got a question? Please don't forget, it's like my memory's been wiped clean from before March the 23rd, March the 17th or something. If I did not scan you your tests and you want it back, unless I get this big burst of energy to scan more things, I'll put it in an envelope and I'll mail it to you. Okay, so send me your surface address. That way we'll be contributing. The dean sent me a postcard the other day and she said, I thought of you when I saw this card, and when I saw the card, I'm like, why did she think of me when she saw that card? It was a weird card. And she said, but I'm trying to save the Postal Service. I'm like, okay, thank you. So I'll mail it to you if you tell me, if you give me your address, and if I haven't already scanned it to you, because I don't know how much it's going to cost. Those things are lots of pages, so who knows how much it's going to cost to mail it. I don't care. It doesn't really matter at this point. So, okay, question anybody? Okay, you guys have a good day today and tomorrow, and I'll see you again on Friday, and we'll look a little bit more on other kinds of spring problems. I'll see you later. Anybody question or will need to stay, whatever, unless I said I'm going to sign out. Let me look at everybody. Okay, I'm looking at everybody. Okay, question? All right. I will see you on Friday. Bye.